Our first speaker is Dr. Leonard A. Sagan. Dr. Sagan received an A.B. degree from Stanford University in 1950 and an M.D. from the University of Chicago in 1955 and an M.Ph. degree, Master of Public Health, from Harvard University in 1965. Dr. Sagan is presently Senior Scientific Advisor and Program Manager of the Radiation Studies Program for the Environmental Division of the Electric Power Research Institute in Palo Alto. He joined the Institute in 1978 and served as manager of the Biomedical Studies Program prior to assuming his current position in February 1982. Prior to joining EPRI, among Dr. Sagan's activities was 10 years as Associate Director of the Department of Environmental Medicine at the Palo Alto Medical Clinic. He also worked as a physician in nuclear medicine for the U.S. Atomic Energy Commission and directed medical research for the Atomic Bomb Casualty Commission in Nagasaki. Author of numerous papers, Dr. Sagan is developing a program in environmental carcinogenesis and other occupational hazards. His special research emphasis is on the radiation effects of nuclear power generation. Ladies and gentlemen, Dr. Sagan.
Good morning. Marvin said very nicely in about 1 minute what I plan to expand on in 25 minutes. So to make a short story long, this issue did begin 20, 30 years ago with these reports from the Soviet Union regarding possible health effects to linemen and substation workers. That led to both epidemiological as well as laboratory studies throughout Europe and North America, which were primarily directed at effects of electric fields. Could I have the first slide, if you'll turn the machine on, Mr. Johnson, please? Those studies, I think it'd be helpful if we could turn down the house lights, at least partially. Those studies were conducted on a number of species, and the results were, as you see on this slide, largely negative, and led to a conclusion a few years ago that this exposure to electric fields were not likely to represent a significant threat to human health. And then again, as Mr. Klinger has said, all of that seemed to change in 1979 with a study which suggested that magnetic fields were potentially harmful to health, and with particular respect to childhood cancer. Subsequently, that is in the subsequent 10 years or so, there have now been in the order of a few dozen studies directed at trying to better characterize the relationship between exposures to magnetic fields and human cancer. The studies can be classified into two groups, as shown on this slide. Studies primarily directed towards childhood cancer and the magnetic field exposure received in homes. The prototype of these studies was, as Mr. Klinger said, the Wertheimer-Leeper study, which I'll describe in a bit more detail in just a minute or two. The other group of studies have been directed towards adults and leukemia, a relatively infrequent kind of cancer. And these studies, as the slide indicates, or many of the studies were based on the assumption that persons in certain electrical occupations, like electricians and electrical engineers, were persons at higher exposure, and so their experience with leukemia was interpreted as indicating that magnetic fields might be causative in producing that disease. Now, I'll show you a summary slide of those studies as well. I do want to start with a slide or two about childhood cancer because it is, fortunately, a relatively rare disease and one with which most people are unfamiliar. So just a word or two about that disease. As you can see from this slide, cancer is by far the most common among elderly people, rising with age as shown here, but it does occur among children in the United States at a rate of about 1 per 10,000 children. The disease is not only less common, it's of a different nature in children than in adults. You see the kinds of cancer that occur among children. The numbers in the right-hand column are the cases per year in the United States, the most common, leukemia, and then a variety of other rare cancers of the eye and of the bone and so forth. Another characteristic of these cancers is that many of them, some people say all of them, have a strong genetic component. For example, Down syndrome. Children with Down syndrome have which is a genetically inherited disease, have a tenfold risk of leukemia compared to children without Down syndrome. But in spite of the fact that it's a rare disease because mortality is uncommon among children, it is the second commonest cause of death among children following accidents from automobiles, drownings, poisonings, and so forth. Before I describe some of the epidemiological studies, I did want to say a word about the interpretation of epidemiological studies. What you see here are certain criteria that are used by epidemiologists and others to make some judgments about whether exposures to agents like magnetic fields cause a disease like cancer or not. I'm not going to dwell on this because Dr. Baylor is going to spend a good deal of time talking about causation, how one makes judgments about whether an association is causal or is spurious. But I do want to call your attention to the importance of exposure assessment. Epidemiological studies are conducted by comparing exposed groups, by comparing the incidence of disease or mortality among exposed groups of humans with those who are unexposed. And then the differences in incidence can be attributed to that exposure if confounders and if other characteristics are present. Exposure assessment. We understand the relationship between smoking and lung cancer because we know who's exposed and who's not exposed. It's a theme that I'll keep returning to because, in my view, one of the weaknesses of the epidemiological studies that I'll describe is that they depend on rather weak surrogates for exposure. After all, we're all exposed to magnetic fields, and the question for the epidemiologist is to define who are exposed and who are not exposed, and that has been done, at least in the past, rather poorly. Other criteria used, and I presume Dr. Baylor will talk about these too, in judging causation is whether studies are consistent. I've just mentioned lung cancer. If you see that smoking and lung cancer are associated in Los Angeles and Chicago and Tokyo and Nairobi and Buenos Aires and Cairo, that builds confidence that this is a really meaningful relationship. And plausibility refers to the question of whether or not there is a biological mechanism that's been demonstrated to explain how exposure produces disease. Now, turning to the studies themselves, the first, the Wertheimer-Leeper study, was published in 1979 in the American Journal of Epidemiology. It was conducted by Dr. Nancy Wertheimer and Mr. Ed Leeper, who set out to test whether children with all forms of cancer living in Denver identified from death certificate diagnoses as dying with cancer, whether they experienced more magnetic field exposure than did a comparison group of healthy children. They did this by assuming that the power lines passing by the children's homes were an adequate surrogate for the exposure of the children. They developed a code shown here, which was based on the assumption that high currents produced high magnetic fields and low currents, such as at the end pole, produced low currents and therefore low magnetic fields. And this information, this code, together with the measured distance of the house to the line, served as their index of exposure. They call these current configurations, beginning with high current configuration, rather very high current configuration, ordinary high current configuration, low current configuration, and so forth. And then they compared children with and without cancer to determine how those homes were distributed with respect to the current configuration, that is, the alleged magnetic field exposure. So that, for example, did that light ever show up? No. So that, for example, for very high current configuration, 6 children were found to live in such very high current configuration homes, and all of these were cases. None of the control children ended up living in such homes, whereas in the very low current configuration homes, there were 65, about 31% of the children were children with cancer. And you see in the right-hand column a fairly smooth gradient, which led them to believe that their hypothesis achieved some validity. The children living in very high current configuration homes appeared to have a significantly greater risk of having cancer than did children with low exposures living in very low current configuration homes. As Mr. Klinger again said, there were loopholes found in this study. For example, the investigators knew which homes were cancer homes and which homes were not cancer homes, so there was at least the opportunity for some unconscious bias in assigning the home as a high or low current configuration home. That study was followed by a number of others, studies of childhood cancer and magnetic field exposures. Within the following year, a study was conducted in Rhode Island by Drs. Fulton and Cobb, this time a study of leukemia alone, and in this case, no relationship was found between alleged exposures and the risk of leukemia. So at that point, 1981 or 82, the score sheet seemed to show one positive and one negative study. The Tumenia study conducted in Stockholm was sort of a maybe. It did show a higher risk of cancer among children living beneath transmission lines, but there was a gradient, so that children directly below the lines showed a lower frequency of cancer than did children living on the edge of the right-of-way. These studies were not convincing to anybody, and what was needed was a more rigorous study, and the Savitt study was rather eagerly awaited because it did attempt to correct many of the problems to which I've alluded. For example, in addition to using proximity to power lines as a measure of exposure, Dr. Savitt also used an instrument to measure magnetic fields and electric fields inside the homes of children. These were not the same group of children studied by Drs. Wertheimer and Mr. Leeper in Denver. This study was also conducted in Denver. These were children who were alive. They were identified from cancer registries, and so there was the opportunity to interview families and to ascertain information about socioeconomic status, about smoking behavior, and other factors which might have contributed to that association between current configurations and cancer. His results are in part shown here. The study was just published this month in the American Journal of Epidemiology, but the results have been widely known for well over a year. It led to those reports in the New York Times and elsewhere last summer that first brought national attention to this issue. He's collapsed his exposure categories so that there are only two, non-exposed and exposed, and that column with the heading OR refers to odds ratio. It's a device used by epidemiologists. What one does is to set the risk of disease equal to 1 for persons who are little or non-exposed, as is shown here, and then the risk of the exposed group is shown as a multiple of that. So what this study says is that there appears to be a 74% increase in childhood cancer for children who live in high exposure homes. CL are the confidence limits, 0.97. You see the confidence limits are quite wide because the numbers of cases here are quite small. You remember that, and from the last slide, or I'll remind you that the study started with 370 or so children. You see only 123 remaining here for this analysis. That results from the fact that many families had moved, could not be located, or they were living in homes where the disease, to which they had moved after the disease had developed, or they had moved to that home only shortly before the disease developed, so that if you limited the study, as shown here, to those cases where the children had lived for at least 2 years prior to diagnosis, the number becomes rather small, and so the wide confidence limits. If you look at the results for leukemia alone, the odds ratio appears to be somewhat higher, but the confidence limit's wider because the numbers are even smaller. Now the next slide shows the relationship between risk and magnetic fields as measured in the homes with a handheld instrument, magnetic field dosimeter. The highest exposure homes were more than 2.5 milligauss, and if you look over again at the odds ratios, although some of you may see a gradient from 1 to 1.2 and 1.3, here the precision is very low, the numbers are small, and the confidence limits very wide. I think the only fair way to read this is that there is no measurable relationship between measurable magnetic field exposures and the risk of cancer. What does that mean? There are two interpretations of that. One group of people says this proves that the association between proximity to lines and childhood cancer must be related to something other than magnetic fields. Surely it's not the magnetic fields. Another group of people says, taking the opposite view, Dr. Wertheimer is one of these, says that an instantaneous measure in a home is a very poor measure of a child's lifelong exposure. The power lines passing by the home, which are stable, is a better measure of lifelong exposure. That question then, which of these explanations is more correct, is yet undecided. But I'll show you later some slides which demonstrate the great variability which exists in magnetic field levels. Moving on, to adult studies, I mentioned the Stevens study because it was the other study, together with the Savitz study, supported by the New York Power Lines Project. And it too was just published this year, this month. It's viewed by the author as being a negative study. There was no relationship either between current configurations or measured fields and the risk of leukemia in adults in Seattle. Do you remember in an earlier slide I mentioned that there are two classes of studies, childhood and adult, which have contributed to this suspicion that magnetic field exposure may produce cancer in humans. The studies in adults, as I indicated before, many of them were based on the judgment that people in so-called electrical occupations could be adopted as persons representing high magnetic field exposures, and so the experience of leukemia in this group could reflect the consequence of exposure to magnetic fields. A number of such studies have been done, and Dr. Savitz has done us the service of aggregating the results of those studies in this one study. And the most important table is shown here. You see what the occupations are. RR, risk ratio, can be interpreted in the same way as the odds ratio, so that, for example, the 2.4 shown after electrical equipment assemblers indicates that for that people with that job title, there is a 2.4-fold risk in leukemia. And again, you see confidence limits in the right-hand column. And overall, the aggregate down in the bottom, shown in yellow, for all of these occupations is 1.2. That is, there appears to be a 20% increase in risk of leukemia among these people in these job titles, with confidence limits just exceeding 1. Welders are interesting to me because they do clearly have high exposures, and yet their risks seem to be less than or equal to those of persons in non-electrical trades. Problems with these studies are, first of all, that nobody has yet measured exposures. We can't confirm that people in these various occupations are at increased exposure, although it seems reasonable. Nor do we know that the persons with leukemia were persons who had increased exposures. Nor do we know that there weren't other factors in these jobs, in the work environment, that might not have contributed to leukemia among the men and women in these jobs. Nevertheless, it's suggestive, and added to the childhood experience can be interpreted as suggesting that exposures to magnetic fields are carcinogenic. To begin to summarize my own personal views about this group of a few dozen studies, some of which link magnetic fields to cancer, some of which do not. I haven't shown you the negative studies. Negative studies do exist. My views about them all is that, first of all, exposure ascertainment has been poor. The children living in so-called high current configuration homes are assumed to stay in those homes, in the same homes, throughout their lives. The loads on the lines are assumed to be constant. The child is assumed not to leave the home or to have any other exposure in the home. It's assumed that there are no other conditions in the home, such as the wiring or grounding of the home, that influence the exposure in the home. And in the case of adults, the adult cases, the job itself is assumed to imply a greater or lesser exposure. And to my mind, and I think to most people, those are very poor measures of exposure. And I don't mean to indict the investigators. The truth is that until recently, there have simply not been adequate instruments with which to measure exposures to individuals. I'll show you a little bit something that we at EPRI have developed, hoping to improve that. By weak risk estimates, I refer to the fact that the increase in risk among the exposed populations, even in those studies which are positive, are small. As you saw, the increase in risk among children was in the order of a twofold increase. Now, to epidemiologists, a small risk estimate of that magnitude is one to be regarded with a good deal of skepticism. It's only when the risk estimates rise to a factor of 10 or 20 that one begins to take serious notice. For example, I've mentioned cigarette smoking and lung cancer twice. The risk estimates for cigarette smokers, the risk of lung cancer in cigarette smokers is 20, 30, 40 times what it is in non-smokers. A weak risk estimate, as I've shown you here, only 20% increased for adults in electrical occupations, is in the noise level. It doesn't mean it's not a real risk. I'm not making that conclusion. I'm just saying that because the risk estimates are weak, one has to be very cautious about accepting these as indicating causation. It's too easy for other factors, confounders, to influence outcomes with such weak risk estimates. Finally, no biological plausibility. Many persons, not all, I think Dr. Adey will contest this in his remarks, but most people feel that it's unlikely that electric and magnetic fields could produce tumors, cancers in humans, for a couple of reasons. One is that for most known carcinogens, chemical carcinogens or ionizing radiation, we know what the mechanism is. It results from damage to the chromosomes, to the genetic material of the cell. Magnetic fields do not produce genetic changes in cells. And so if magnetic field exposure is carcinogenic, it must be through some other as yet unknown mechanism. So again, that doesn't prove that magnetic fields are not carcinogenic. It just makes one more skeptical about that. What are we doing at EPRI? I hope there's 5 minutes for a little propaganda. 4 minutes. Our program is based on 3 parts. Epidemiology. Is there a risk? The only way one will know this, or one important way in which one will know this, is by conducting more and better, more rigorous studies of human populations exposed to magnetic fields. And we're doing that. I'll show you a few examples in a minute. Secondly, through the development of better instruments and studies conducted by our division as well as Frank Young's division in electrical systems, we're trying to understand those factors that determine magnetic fields in the work and home environment so we can identify populations who are exposed, principally for the purpose of conducting better epidemiological studies. And thirdly, we have a program in basic sciences in which we're trying to better understand how magnetic fields and electrical fields interact with cells to produce changes in cells. And there are changes. What the significance of those changes is to my mind, yet uncertain. Here are some examples of studies that are underway at EPRI and the dates at which we hope to see them completed. 2 of those studies, telephone workers and utility workers studies, are studies of persons who are occupationally exposed. Telephone workers refers to the linemen or splicers who are on poles or in manholes splicing who are at some increased risk of exposure. Do they have increased risk of leukemia? The early results from that study being conducted at Johns Hopkins appear to show that they do not. Utility workers study, electric utility workers study. There are 5 utilities now participating in a pilot study with us. This study is being conducted by Dr. David Savitz, again at the University of North Carolina. be completed by 1990. We're examining childhood cancer in Los Angeles. Dr. John Peters at the University of Southern California is studying leukemia in children, their proximity to power lines. He's also conducting measurements of exposure with the MDEX, the instrument that I'll talk about in just a minute. We're going to initiate studies in animal populations to test whether animals in a laboratory exposed to magnetic fields show any increase in cancer. My last two slides, because I'm proud of these are records obtained with the MDEX. Our dosimeter, which is about the size of a pack of cigarettes or two, can be worn on the waist. This is a record obtained from a young 8-year-old girl who wore this for 24 hours, and you can see, even from the back of the room, enormous variability in her exposure. She comes home from school in the middle of the afternoon. She's in the home. Exposures recorded are about 2-3 milligauss. She goes to sleep under an electric blanket the next day in school. A number of spikes which result from passing near electrical equipment. We assume we don't have detailed data on her history that day. But this is just meant to reflect, or what it means to me is that knowing only the exposure in the home tells you only a tiny part of a person's exposure history. What one wants ideally is this kind of information over long periods of time to properly characterize exposure. And this, my final slide, to show you that homes differ considerably, both in the intensity of exposures as well as in the temporal changes that occur over the course of a day. Two different homes. One shows a distinct diurnal variation, probably paralleling changes in the loadings on the adjacent lines. And to close, of the Electric Power Research Institute, my closing slide. Thanks very much, Mr. Klinger.
Our next speaker is Dr. John C. Baylor. Dr. Baylor is a native of Urbana, Illinois, a town that's near and dear to my heart, having gone to school there. He received his Bachelor of Arts degree from the University of Colorado and an MD degree from Yale University. He also holds a PhD in mathematical statistics from the American University. Dr. Baylor is a scientist in the Office of Disease Prevention and Health Promotion of the Department of Health and Human Services at this time. He is a professor of the Department of Epidemiology and Biostatistics at McGill University School of Medicine and a staff member, Health Effects Institute, Cambridge, Massachusetts. Has numerous honors and has published extensively. With that, I give you Dr. Baylor.
My topic is Science and Uncertainty, Biostatistics and Epidemiology in the 1990s, and with a special focus on the topic of the plenary session as a whole, electromagnetic fields perspectives. If you look at those carefully, you'll see this gives me license to talk about anything I want to. What I plan to do here is to talk about some rather broad matters having to do with health effects and exposure to power lines or exposure to electromagnetic fields generally. I specifically disclaim any special knowledge about specific health effects and specific exposures. I'm more a methodologist. I have a strong special interest, quite broad interest, in how people go about learning from data, generally from imperfect data. And I've been an interested observer of this whole set of discussions in recent years about biologic effects and electromagnetic fields. As a general observer of this field, I've come to a few conclusions which I hope you will find helpful as well as interesting. The place to begin, I think, is with a little couple of definitions about statistics and epidemiology. Specialists in these fields argue endlessly, of course, but in my set of definitions, statistics is the art and science of inference under uncertainty. You may have other definitions. A lot of people would define statistics in terms of collections of data. Baseball statistics, the statistical abstract of the U.S. Other people define statistics in terms of mathematical theory. Still others in terms of experimental design and the interpretation of individual studies. But I'm taking now this broader notion that statistics is to be defined as the art and science of inference under uncertainty. More generally, or more specifically rather, epidemiology I will define as the branch of applied statistics that deals with the determinants and correlates of human disease. It's related, of course, to the word epidemic, but there are lots of extensions and changes in meaning as we go to this term epidemiology. But I think it is basically a branch of applied statistics as I have defined it at the top. We're going to be dealing with uncertainty. I know a lot of people think of science as being the field of certainty in the extreme, certainty par excellence. My view is quite different. I think of science as being focused on uncertainty. And as soon as something becomes certain or virtually certain, it moves out of the area of great interest in science and into something else. Well, I said that I had some general observations. First, I would like, though, to illustrate some epidemiologic links of various kinds of exposures, primarily environmental exposures, to human health outcomes. Some of these, I believe, are quite solidly established. Now, let me explain also, when I talk about solidly established, I'm trying not to give you my opinion, but the opinion of those experts who work in the field generally. And some of those that appear to have achieved virtually complete consensus among experts and to be based on very sound data that can't be seriously questioned when the data are examined as a whole, are the health effects of some industrial carcinogens. I've listed vinyl chloride and asbestos, the health effects of cigarette smoking and lung cancer, the fetal alcohol syndrome. It's a fortunately uncommon condition that's found in infants among mothers who drink alcoholic beverages, generally to excess during pregnancy. I think all of these, the evidence is virtually incontrovertible. There are a few others, in fact a lot of others, I've just listed a couple here, where it's not entirely established, but the evidence is very strong indeed. And a couple of examples I put up here are diet and heart disease, specifically the effects of cholesterol and fat in the diet. I'm actually talking about fat that you ingest, not fat on the body, not obesity, but the consumption of fat. And the health effects of passive smoking, where the evidence, I think, is strong, as I've indicated here, but not as strong as it is for the active smoking that goes on in people who smoke cigarettes. We might say that the evidence, as judged by the whole scientific community, is fair, doesn't reach those standards for some other things like salt and hypertension, diet and cancer, particularly cancer of the breast and large bowel, and altitude and reproductive problems. We find that reproductive problems are more common, tend to be more common in people who live at high altitudes, miscarriages, certain kinds of fetal losses, birth weight tends to be a little lower and so forth, but this is a bit iffy. At the bottom, you'll see I have put low-level exposure to electromagnetic fields, where the evidence is poor, as judged by the scientific community as a whole. I'm not trying to give you my opinion about this. But as Dr. Sagan said, I would repeat, this does not mean the effects are not real. The evidence is not yet judged by the scientific community as being terribly convincing. And it's part of your job and mine, at least for some of you, to work on this a bit more and try to reach the point where we can say yes or no and move that a good bit further up in the list. Thank you. What are some of the things that we need to improve this situation? What can we do collectively? And I think as an interested observer, I've observed a number of other fields where there have been a lot of questions about health effects, that this area really needs some substantial attention to three different matters. And this is going to take some kind of leadership that is not yet in evidence in this particular field. I'm not knocking the efforts of individual investigators, some of whom are very strong and have done first-rate work. I'm talking about leadership of the field as a whole. The first thing you need, in my view, is a broad conceptual model about how to draw inferences regarding electromagnetic exposures and human health. I'll come back to this. I'm going to spend most of my time here talking about what I mean by a conceptual model of this, but it's not yet in evidence, at least not to me. What you have is a lot of fragmentary observations, a bit here that says yes and a bit here that says no, and then somebody else comes along and says, no, you're both wrong, it's in between, and we find peripheral evidence brought in that bears only partially on either of these, that may alter some interpretations, and you need an organizing principle. You need a way to put this all together. A second thing that I think you need is what I call anchors, at least a few of them. Solid demonstrations that effects do or do not exist at low exposures. By this I mean demonstrations related to very specific kinds of exposures in terms of the specific exposure. Is it electric or magnetic or air ions or whatever? Specific energy levels, if that is considered to be a possible issue, and specific endpoints. It's not enough, for example, to say that some kind of exposure is related to cancer. You need to get quite specific about what kind of cancer and sometimes in what kinds of people. A clear distinction there is children versus adults. I'll say a little more about that. And then the third thing is to have a rational way to set priorities for future work. And this will depend on both of those first two things. I am not aware at this time that there is any general consideration, broad consideration, of how to set priorities for where the greatest part of future attention ought to be focused in trying to determine matters of human health in relation to this whole set of exposures. A little background before I come back to dealing specifically with conceptual models. Epidemiology, as this branch of applied statistics, is inherently descriptive, not experimental. And that means that as soon as you go to epidemiologic studies, you'll be doing without a lot of the things that some of you have come to depend on as the core of science. Things like randomized allocation, or at least semi-random allocation of subjects to distinctly different treatment. Control of extraneous variables is generally not possible. Replication is often utterly out of the question. As epidemiologists, we have to go out and observe what we can and then try to interpret that data, but recognizing that we don't have a lot of the most critical tools available in other kinds of science. A second general point is the need to recognize that some questions about human health can be answered by epidemiology and some simply cannot. And I think it would be a step forward to have a clearer delineation in concept among those who have to deal with the outputs of these studies about where epidemiology can be helpful and where it can't. There's a rough rule of thumb in the field, and it is quite rough, that it's awfully hard to establish an effect by epidemiologic means when the relative risk is less than about 2 to 1. Unless there's at least a doubling of risk, there are always going to be a lot of questions about the comparability of the groups and about the exposures and one thing and another, so that you won't reach a definitive conclusion. A third general point is the need to look at the whole of the record. And in my casual observations, I've seen a good many violations of this. People with one or another axe to grind who look at the positive evidence, other people who look only at the negative evidence. They each attack each other with more vigor than they attack their own side of the argument. And as a scientist, I think that's a mistake. We have to try to assemble the whole record first and then look at the whole thing even-handedly, objectively, and pretty carefully. The fourth general point in this field has to do with data. I could expand on this all day, but you'll be glad to know that I don't intend to do that. The data available in an overall assessment of health effects and environmental exposures, including what we talk about here today, tend to be extensive, complex, of poor quality, and not often precisely targeted for the purpose at hand. For example, in the initial studies in Denver of childhood leukemia, we didn't have incidents of leukemia, we had deaths. We did not have direct measures of exposures, we had wiring codes and that sort of thing. That's what I mean by the data are not precisely targeted. We don't have what we really want to have. This is particularly true when one has to use existing records for various things. Well, we don't have time to dwell on that. I'd like to go now to an example of a model. This was also mentioned very briefly by Dr. Sagan. I'm going to suggest two kinds of models, simply so you'll know what I mean, that you won't go away thinking, gee, that's nice, but an airy suggestion. I'll show you two specific kinds of models that have a good bit of relevance here, but may need to be modified. The first one is a model now generally accepted for quantitative health risk assessment. First articulated by a committee of the National Academy of Sciences. It's been developed and extended and modified in various ways by a lot of other people, including myself. It begins with a definition of what we mean by risk assessment. That is, the quantitative or qualitative estimation of the likelihood of adverse effects from exposure to specified health hazards or from the absence of beneficial influences. Definition like that, you can look at and say, well, gee, what's in that? In fact, that took a committee a good part of a couple of days to evolve, because there are lots of implications, nuances in each of those words. I'm sure you've seen this sort of thing in your own fields. But anyway, it's now, I think, an often accepted definition of risk assessment. There are in it 4 steps in this particular model. The first of these is what's called hazard identification. That is, the qualitative indication that a substance or condition may adversely affect human health. This is the initial determination that there is really something there to worry about. And many risk assessments get stuck right at this point. There are indicators that there might be something to be concerned about, but the indicators are not sufficiently strong to suggest the need for going further. A second step in this general process is hazard characterization. That is the quantitative and qualitative evaluation of the nature of the adverse effects, including their expression as functions of the amount of exposures, that is, dose-response relationships. Some kinds of exposures, of course, have a long plateau. Nothing much happens until you reach some minimum level, and then they take off and go up rapidly. Others may have an initial rapid increase. The first little increment of exposure gets almost everybody or a large part of the population, and then further exposures don't add very much to that. There are all kinds of other things in the way of dose-response curves, but that's a part of this. Another part of hazard characterization is to characterize those persons who are at special risk, either high or low. It would include the determination that children are unusually susceptible, or that children are resistant, that pregnant women are a matter for special concern. It would include the assessment of the evidence regarding synergies in effect. Are people who have had in the past or currently have some other kind of exposure likely to react in abnormal ways? All this comes under the heading of hazard characterization. The third step in this model of risk assessment is what's called exposure characterization. The qualitative and quantitative evaluation of the degree of human exposure likely to occur. And this generally includes a good bit more than the average or mean exposure. If you have a first-order effect, of course, it doesn't much matter how that exposure is distributed across a population in determining total risk. If you have anything other than first-order, it may matter a lot. And even with a first-order process, it can matter a lot who is exposed, how much, if there is substantial concern about distributional effects. If you have, for example, a first-order effect that is focused on, in which the exposure is focused on some group of persons of special concern, like children, you may still need to know the distribution of exposure as well as the average or the total. The last step in this particular conceptual model is called risk determination. That is, the integration of these first three steps into a scientific determination of the level of risk as a basis for policy consideration. And that last line is critical here. We're not playing intellectual games. We're dealing with some pretty serious matters. We want some pretty serious things to happen. When we find that there is or is not a clear conclusion, pro or con, and so the focus throughout all of this should be on policy. There is one way in which you can organize your thinking about human health effects and exposures of the kinds we're talking about here. And it is, in fact, very helpful to have this sort of structure. I've compared a lot of risk assessments of chemicals, mostly, that were done before this model became widely used, with those done later, and the improvement in quality of the risk assessment, the improvement in reliability and defensibility of what's concluded is really quite astonishing. There are a lot of sub-steps in these that people have developed I've not talked about, but the fact that we now have a generally accepted way to organize this huge mass of information has in itself provided a substantial advance. I'd like to show you a different kind of model that is in no way inconsistent with this. It's simply another way to organize a huge amount of material. It was also referred to in passing by Dr. Sagan has to do with causal inferences from observational data and is generally traced back to Bradford Hill, perhaps some 25 years ago. They are strictly empirical criteria, 6 of them. Again, there's been a lot of modification, development of these. This is not Hill's original statement, but one that I happen to simply lift out of a report on diet and health. But I think they apply here just as well. One of the things to consider is the strength of an association. The stronger the apparent association, the more likely it is to be cause and effect. There are a lot of exceptions to that, of course. You have to be very careful. But you would ordinarily expect to find a stronger association with a causal effect than with one that is simply random or in some way adventitious. You would expect to find a dose-response relationship. That is, that the response increases with increasing dose. And if you don't find that, if the response goes up and back down, or if it goes up and flattens out, then you should think a second and third and a 10th and a 20th time about whether that's really causal. It can happen. There are some good examples of how it can happen and good biologic mechanisms. But failure to find a dose-response relationship is generally considered a sort of mark on the negative side that will have to be balanced somehow by better evidence on the positive side. And the third thing is fairly obvious. Things have to be in the right temporal sequence. If the purported effect is observed before the cause, then you've got a real problem in drawing a cause-effect relationship. If the purported effect is observed too soon after the purported cause, you still have a problem. For example, most cancers have a latent period of at least 10 years after exposure. I'm not counting childhood cancers, but the common kinds of cancers in adults, it's generally considered most of those take at least 10 years from the start of exposure until something is detectable. And if you find a report that's counting cancers in the last 5 years or 3 years or 2 years, then you might wonder whether the temporal relationships, the temporal sequence, have somehow gotten out of line. Those first 3 can be applied to single studies in your evaluation of the evidence as a whole, but they are applied also to the evidence in its entirety. The last 3 here apply only to the evidence as a whole. One is the consistency of the association. If you find a relationship, for example, between childhood leukemia and exposure to magnetic fields or electric fields in Denver, but you don't find it in Boston or Stockholm or Rio or a lot of other places, then you wonder why. If you find the same kind of thing in a lot of different sorts of studies, then it's more likely to be causal. If you find it, for example, in follow-up studies, what are called cohort studies, and case control studies, and cross-sectional examinations of human data, if you find it in animal studies and clinical studies and even other ways, then you may tend to have a stronger belief that this association is one of cause and effect. The specificity of the association is a matter of some concern. If you find that some specific kind of exposure is related to an increased incidence of cancer and birth defects and heart attacks and depression and a lot of other things, then you ought to begin to worry about it as whether it's really cause and effect, or whether it might instead be that the exposed persons are generally susceptible to disease for other reasons and happen to come into your study because of that. The more specific the association observed, the more convincing it can be with respect to cause and effect. Again, it's not an absolute, but it can help you along. And the last point, again, not an absolute, is biologic plausibility. Are there good biologic reasons for thinking that this kind of effect might be related to the exposure you're looking at? If so, you're a bit further along toward making an inference of cause and effect. If it seems biologically not plausible, then you have an extra hurdle to overcome in these other things. Well, again, a great deal could be said about this model. It has been applied in a very wide range of circumstances. The first time I came across it was about 25 years ago when it appeared in the Surgeon General's report on smoking and health. Did just fine there. It's done fine with the diet and health. It's done very well with some kinds of industrial health hazards, a whole range of things, and might be adapted here. I'm not pushing one or the other of these conceptual models. I don't know if either of them would particularly well fit this field. What I'm suggesting is that the field as a whole needs a conceptual model, maybe one that's specially developed, as a way to organize your efforts, organize your thinking, organize the information you already have, and come to some generally agreed principles about how conclusions are going to be drawn.